Hello, welcome to the LinkML Community call for March 19th. We have our good news that the paper is finally out. We've had a lot of activity in LinkML, our merge repository with runtime included, and in LinkML map. Yeah, 74 PRs created, 39 merged. Got to get ahead on that trend. And amazingly, like 28 authors, 13 reviewers, issues 82 created, 31 closed. Again, it does feel like it's going to put us behind, but and then the 47 unique contributors in the last month is just astonishing. And I'm not going to read all the content on these, but a whole bunch of work on generators, infrastructure, and LinkML map. LinkML map especially has its new releases out. Going to that this week. We have office hours coming up, which is the basically where you can just hang out with a core developer. And I think Corey and I are going to take turns on that. And we can help you out with like accomplishing whatever it is you want to like fix or improve in LinkML during that time slot. It's going to be the first Thursday of the month, 2 p.m. Pacific time, 10 p.m. I don't know what BST is. I think that's anyway. That's our Zoom link. And just move on that like Sarah is the community outreach coordinator, and that she should contact for presenting at the LinkML calls and any other outreach connections. So Damien is up first with an introduction to LinkML-Java.
So shall I go ahead right now?
Yes.
Oh, yeah, sure. Okay, do you see my screen, my slides?
Yes.
Yes.
Great. So thank you for the invitation to present today. So I will first start with a very quick introduction to German bioimaging, since this is the first time we are presenting at the LinkML Community call. So German bioimaging, or GERBI, is a German scientific society for microscopy and image analysis, whose purpose is broadly to support the use of bioimaging techniques throughout Germany. And that remit includes contributing to the imaging software ecosystem through our research software engineering unit, to which I belong. And that unit is notably a member of the Open Microscopy Environment Consortium, which is in turn responsible for the development of several key software in bioimaging, such as the Homero server and clients and the bioformats library. Among the projects that GERBI's LRC unit is working on, at least 2 are using or will soon use LinkML. One is OMISAR, which is a new imaging file format that is especially intended to represent and manipulate extremely large images. And the LinkML will be used to define the model and format of at least some of the imaging metadata in OMISAR files. And the Imaging PhD, a related project aiming at defining a new imaging metadata model that would allow to capture much more details about the hardware that was used to acquire an image compared to what our present models are doing. And the new model will be formally defined as a LinkML schema. So both of those projects will require the ability to seamlessly work with LinkML-defined instance data in more languages than just Python, including Java, which led us to start the LinkML-Java runtime library as a preliminary step. So first, why do we even need a runtime library for LinkML? Using LinkML Python, we can already generate Java classes that will represent a LinkML model. And so with that, we should be able to use a standard JSON or YAML library, such as, for example, Jackson, which is a very popular library in the Java world. So a standard JSON or YAML library to easily deserialize a JSON or YAML file into an instance of the Java class that represents a LinkML class. And from then, we should be able to manipulate that object as any other Java object. So we should have already everything we need, right? Well, no. Using a standard non-LinkML aware library would work, but only with the most simple schemas. Not simple in the sense that they don't contain a lot of classes, but in the sense that they don't use any LinkML specific features. And I will show you two real-world examples. The first one is the Knowledge Graph Change Language, KGCL. That's a LinkML model that describes edit operations on a knowledge graph or an ontology. And it does so by having more than 50 classes that each represent a specific type of editing operation. So for example, you would have a class to represent the renaming of a node, a class to represent the replacement of a predicate by another, a class to represent the addition of a synonym, etc. And all those classes are grouped under a generic change class. A typical KGCL file like this one will typically contain one or several instances of any of those classes, but crucially, we don't know in advance the exact type of each of those instances. We only know that there will be instances of some subclasses of change. The exact subclass has to be discovered at runtime by looking at the value of the type slot, which has been defined in the KGCL model as the type designator for the change class. For example, we know that the first object here is an instance of the node rename class because that's what the type slot tells us. But a generic YAML deserialization library does not know what a type designator slot is. If you ask, for example, the Jackson deserializer to deserialize that file as a list of change objects, it will predictably expect to find instances of the change class, which means, for example, that it will not know what to do with the old value and new value slots because those slots do not exist in the change class. They are only defined in the simple change subclass. The other example is LinkML's own meta schema. A class definition in LinkML contains, among other things, a slot called slots, which is expected to contain the list of slot definition used by the class. This will be rendered in Java, unsurprisingly, as a class definition class with a field typed as a list of slot definition. But in the YAML serialization of a LinkML schema, the content of the slot is serialized not as a list of slot definition objects, but as a list of names, each name being a reference to the actual slot definition, which is stored elsewhere in the YAML file. So that is completely normal, and this is due because first, a slot definition is defined in LinkML as being a globally identifiable object, meaning that the slot definition class has an identifier slot. And secondly, the slot is not defined as being inlined, which means that its values are expected to be serialized by references instead. So this is all standard LinkML behavior, but again, a non-LinkML aware library will know nothing about all of that. And so a non-LinkML aware deserializer would error out when trying to deserialize a class definition into a class definition object, because a list of names, as here, is not the same thing as a list of slot definition objects. So overall, working with LinkML-defined instance data in Java, or I would argue in any other language, requires support from a LinkML from a runtime library for the same reason that Python developers have a LinkML runtime package. Because merely translating a LinkML schema into a set of classes or whatever can be used to represent classes in your target language is not enough to support all LinkML features. In particular, developers need explicit support for at least the following features, which I believe represent the minimal feature set to work with LinkML data. The notion of type designator slots, the notion of globally or locally identifiable objects, the fact that globally identifiable objects can be serialized as mere references rather than being inlined, the various forms of inlining, list inlining or dict inlining, simple dict, compact dict, and so on. And I would add to that support for not having to explicitly deal with queries. So just to further reinforce the point, so if the code currently generated by LinkML's Java code generator is not enough, couldn't we get away with that solely by making the generator produce more code rather than having to use a runtime library? Yes, we could amend the generator so that instead of producing simple classes that are nothing more than data holders, it produces classes with additional methods that provide all the logic needed to minimally load and dump instance data. Those methods would contain all the logic needed to deal with the minimal set of features that I mentioned on the previous slide. So that will be possible, but I would argue that it will not be practical, and in effect, it will be unsustainable, if only because we would have to develop, maintain, and debug Java code that is embedded within Jinja 2 templates, which are themselves in the middle of a pure Python project. I believe it is much better to keep the generated code as simple as possible and deport most, if not all, of the logic needed to work with that code elsewhere in a separate runtime library. So now I will go through some of the design decisions that informed the development of the LinkML Java runtime. The first and arguably the most important decision is that the runtime must not require the schema itself in order to be able to read or write instance data. It must be able to work with nothing more than the code that was generated from the schema without the schema itself. This makes bootstrapping much easier because it dispenses us from having to develop a full-blown custom LinkML parser when all we want to do at first is to parse instance of a schema. We are not interested in the schema itself, at least not at this stage. In the future, the library will probably offer additional features that may require runtime knowledge of the schema, but the basic features of loading and dumping LinkML-defined instance data must be doable without such knowledge. The second decision is a direct consequence of the first. Since we do not have the schema at runtime, it means that we must rely solely on the generated code to provide us with all the information we need to be able to read or write instance data. So the generated code already tells us what are the slots and their range, so their type within a class, but we also need to know, for example, which slot is the identifier slot, if any, which slot is the type designator slot, whether a slot is expected to be inline, and if so, in which form, or what is the URI associated with a class or a slot. And so this is done through a set of dedicated Java annotations that needs to be added to the generated code, as in this example here. And so part of my work in the previous weeks has been to amend LinkML's Java code generator so that it could automatically inject those annotations. And there is a PR in a review that does precisely that. Somewhat less important decision is that the runtime must not depend on a specific JSON or YAML library. That's because the runtime is expected to be used by several existing projects in the bioimaging community, projects that may already have a JSON or YAML parser among their dependencies, and we don't want to force them to use another specific parser just to work with LinkML data. And so for that, the runtime does not work with JSON or YAML files directly. The typical workflow for data loading, for example, is that you would first parse the JSON or YAML file into a generic Java map structure using any parser that you might want to use, and then you pass that generic map structure to the runtime, at which point it does not matter which parser produce that structure. Next, the runtime must be flexible enough to accommodate the specific needs of some models, including needs that are not themselves defined in their schema, but that are expressed elsewhere. And KGCL again provides us with an example. The old value slot in the simple change class is nominally defined as being string typed, but in fact it has a variable type. Sometimes it will contain a string, sometimes a query, and the exact type is indicated at runtime by the old value type slot. But the loading code in a LinkML-Java runtime would not know about that because this is a KGCL specific behavior which is not encoded in the LinkML model that defines KGCL. So we must be able to request the use of a custom converter object specifically intended to process instances of the simple change class where we can implement whatever specific behavior is needed to process this particular type of object. And lastly, the runtime must allow the developer to completely forget that queries even exist by taking care of automatically expanding them into IRIs upon parsing and automatically contracting them back into queries upon serializing. This is arguably less important in the big scheme of things, but I personally believe that this is a critical must-have feature. As a user of the runtime, I do not want to have to deal with queries. I believe this is fully the job of the runtime. Queries are a serialization detail and should never appear in the core logic of an application. So with that, what can you do currently with the initial version of the LinkML-Java runtime? Mainly, you can load and dump LinkML instance data from and to JSON and YAML files. So for loading, you have both a high-level interface and what I call a mid-level interface. The high-level interface is one that abstracts away all the LinkML details, and that interface can be used roughly in a similar way to the loaders object than Python developers will find in the LinkML Python runtime. In that, you just have to give the loader the file that you want to deserialize and the type of object that you want to deserialize, and the loader will do everything for you. What I call the mid-level interface can be used if either you want to work with data that have already been read from files and put in memory, and if you need finer control about what the runtime will do. Obviously, the finer control will require more familiarity with the inner working of the runtime, which will be explained in the documentation of the runtime, but that I will not detail here. So of course, I'll be happy to answer any question you might have if you do want to go into the details of how the runtime is working. As for dumping, I will not, again, go into the details for that. That's basically, it works very similarly to loading, just the other way around, with, again, those two high-level and mid-level interfaces, depending on how much you want to control what the runtime is doing. So a few things to be aware of about the current status of the implementation. First, about type designators. LinkML-Java currently supports both single and multi-valued type designators. Whether this is a good idea or not, that remains to be seen, because I've learned after having implemented that LinkML Python itself does not support multi-value type designators, and in fact the feature might be obsoleted, so we'll see what happens. In any way, if the type designator is a string, there is one limitation in that it will only work if the designated class lives in the same Java package as the base class. That is the class that holds the type designator slot. This should not be too much of a limitation, as the current behavior of the Java code generator is already to put all the code in the single package anyway. But still, that's something to be aware of. If the type designator is a URI or a query, then the designated class can live anywhere within your Java code, but the runtime will only recognize it if it has been explicitly registered first. So those limitations may be lifted in future versions, but I do not consider that a priority for the time being. Then about referencing, the most important thing to be aware of is that the runtime will automatically resolve LinkML references when a slot contains a name pointing to another object into Java references. For example, if you are working with LinkML's own meta schema and you have loaded a class definition object, what you will find in the slot of that object, which you can access through the getSlot accessor, will not be the names of the slots as it will be in Python. Instead, it will give you directly Java references, what in C++ we will call pointers, to the actual slot definition objects. And there are two reasons for that. First, because this is more convenient. And in fact, I believe that resolving those references is completely within the remit of a LinkML runtime. As a user of the runtime, I should not have to bother resolving those references myself. And second, because Java's strict typing rules actually do not give us a choice here. It will not be possible to store slot names, which are strings, into a field intended to store slot definition objects. So we have to resolve those names into the actual object that they point to. Then about inlining, currently the runtime only supports what the LinkML specification calls non-repair normalization. So mostly that means that if a slot is expected to be serialized as an inlined list, then it will be an error if the parser finds the slot serialized as an inline dict instead, and the other way around. Again, implementing non-repair normalization will probably happen in the future, but not in the initial release. Next, about extra slots, the runtime does support the presence of extra slots if they are allowed in the LinkML schema using the extra slot allowed set to true. So an extra slot, just to be sure we're talking about the same thing, is JSON or YAML keys that do not correspond to a declared slot or attribute for the class that we are currently deserializing. But support for extra slot requires that during code generation, we add an additional field specifically intended to store the values of such slots. So if the class contains that extra field, which has to be a map string object, and if that field is labeled with an extension holder annotation, then when deserializing, any extra slots that do not correspond to a known slot or attribute will be stored in that extra slots field. Otherwise, if the class does not contain a field explicitly intended to store additional slots, then the loader will simply ignore any extra slot it may find in the data. Then lastly, a quick note about LinkML dynamic enumerations. So simply put, they are completely unsupported for now. And this is because as of now, I'm still unsure about the best way to support them in Java. One thing that is already clear is that they will not be represented as actual Java enumerations. The values of a Java enumeration must necessarily be known at compile time, which is by design incompatible with the very idea of dynamic enums. So what to expect in future versions? So obviously there's still a lot to implement, and the roadmap for future versions is not fixed yet, but RDF support, that is the ability to import or export data from or to RDF instead of only JSON or YAML files, will definitely be there at some point, as well as at least some support for dynamic enums. Longer term, the runtime will also allow to work with a completely unknown schema that is only discovered at runtime without requiring that code has been pre-generated specifically for that schema. And once the runtime can do that, then it will most likely at some point include its own code generator, which will make it much easier to integrate the code generation step into the build process of a typical Java project. And that will probably take the form of a Maven plugin, the idea being that you can just add this plugin to your Maven configuration, point it to the LinkML schema that you want to work with in your project, and the plugin will automatically generate the code in the early phases of the Maven lifecycle. And with that, I thank you for your attention, and I welcome any question.
It's super great work, and I'm just in general excited that the little stub of a Java generator that I put in place a couple years ago is like finally getting the love and attention that it needs.
Yeah, I know.
This question.
Yes, I was going to say roughly the same thing. No, this is really fantastic. This is great to see. I yeah, just the part at the end. You know, I think as Kevin says, it was always a long time ago we wrote this how to port LinkML to other languages, kind of like rough guide. And the idea is that you have generators written in Python that can essentially bootstrap the whole process and give you a stub that is enough to kind of like get you started and then build up the framework that you need to kind of like, especially something like Java. For people who don't know, Java already has this rich ecosystem. It's got a heavily code gen kind of culture, I would say, you know, so there's already this rich ecosystem of code generators where you might want, in one particular project, you might want to generate something that is, I don't know, Hibernate annotations or Lombok annotations. So I guess that's my question is that something that would be supported in LinkML-Java? You know, because what you have with the LinkML annotations make a lot of sense, but you can imagine someone's got maybe a legacy Java project that they want to use and it's already, you know, or you maybe want to mix in those with kind of Hibernate annotations sorry, did that make sense?
Yeah, it does. So before answering your question, just a comment about the strategy that is proposed by LinkML about porting. So I did read that page with a lot of interest, and overall, I think it's a very good strategy. But there's one step that is missing in the strategy, is the ability, once you have generated code for a given model, including LinkML's own meta model, what's missing is the ability to load data, to deserialize instance of that data into your, and that is precisely what the LinkML runtime is doing. That's the one missing step in that strategy. And I would argue this is actually, in my opinion, this is the first step that you should consider when you're interested in porting LinkML to other languages. You can use the existing Java code generators in LinkML Python, but then to work with the code that has been generated, you need a small library to help you load instance of a LinkML model into objects that are represented by the code that has been generated by LinkML Python. That's just the one missing step in that porting guide.
Yeah.
So as for yes, working with so for now, there is no code generation in LinkML-Java itself. When LinkML-Java will have its own code generator, it will clearly generate code that is intended to work with the LinkML-Java. Whether it will be flexible enough to also be, whether it will allow, for example, the use of custom templates, probably. For now, that is completely undecided. But in any case, for now, Java code generation can only be done with LinkML Python. There is no code generator in LinkML Java. And the Java code generator is flexible enough that you can very well add your own annotations, annotations from another framework, Hibernate annotations or anything, on top of the annotations that are needed by the LinkML Java runtime. So you will just need to take the templates that are provided by LinkML Python and either copy them and then modify your own copy, or if you're more on the adventurous side, you modify them directly in the LinkML source code. But in fact, one of the things that I did over the past few weeks is precisely to add to the code generator in LinkML Python, add the possibility to use custom templates, what I have called template variants, so that anyone can very easily create their own variants of the standard templates. So they can very easily add their own annotations, their own custom code for whatever it is that they want to be doing.
Excellent. Makes sense. Thank you.
Well, we should probably wrap and move on to Chris's talk. I don't know if it's worth. Yeah, I'll share the introduction slide briefly before we get started on validating dynamic. Like I said, so these are our dynamic enumerations coming back, kind of, and I'll let you get started, Chris.
All right, thank you. Yeah, no, and I think that was a nice kind of segue at the end there from Damien, and we can maybe return to the discussion of how dynamic enums should be represented in different languages. But yeah, so this is about a new part of the LinkML ecosystem, the linkml-term-validator. But before just going into what it does, I thought I'd just give a brief intro about both how ontologies are used or maybe misused in existing data standards, how the LinkML specification has evolved to try and help with that, and then at the end I'll kind of come to the actual kind of like tool chain and how we might actually go ahead and implement this. But many of us here like to make use of ontologies as a part of our different standards and so on. This is just to show that independent evaluations have showed that in fact in a lot of the existing implemented standards, ontologies are either kind of like massively underused or the actual data sets don't make use of these ontologies. So Uberon is an ontology that we developed for being able to describe the source of tissue in a metazoan sample and so on. And this kind of evaluation as part of the CFDA kind of like fair evaluation kind of like showed it was like hugely underused. So what can we do to kind of like help with this? So this is an example of maybe a schema that does not enforce the use of any ontology. And we see this kind of thing a lot of the time where you've maybe got a sample class or a class for something like a nanomaterial. It's got an ID, it's got a name, and then maybe you've got some property for being able to describe the morphology of the nanomaterial. And what many people will do is just say, fine, yeah, we can put a string value in there. But of course, we might want to bind the values of those strings to a fixed list, a drop down of terms like nanotube, nanoparticle, and so on. So of course, you can do this in LinkML. You can do this in pretty much any schema framework, whether it's like most SQL databases and JSON schema. In various languages, there's always this kind of like concept of an enum or a enumeration. And of course, you can do this in LinkML. So you can say, you can restrict this to be a certain set of predefined values. And this is easily, trivially supported in the existing validation framework. This is a good start, but maybe it's not so good for interoperation because maybe I want to interoperate my schema with a group who maybe uses slightly different strings to represent the same concepts. So of course in LinkML, as many of us know, we can attach these meaning fields onto existing permissible values within a schema. And in this case, we say that the meanings here map to terms identifiers from Kebi. And this means that in exchange formats like JSON, you can continue to use more idiomatic kind of like string values like nanotube, but behind the scenes it is treated as if semantically is this Kebi ID. And of course, if you serialize your data as RDF, it will actually be the Kebi URI that is used here. But how do we, one challenge with this is we have many schemas like this, but how do we know that the IDs here are correct? We often manually author our schemas and we maybe are copy and pasting IDs from OLS. It's got a nice copy button, so we shouldn't make typos, but nevertheless, There could be typos in these IDs, or maybe can be changes over time, and we'd like to know if any of these concepts are obsoleted and we need to make some kind of corresponding change within our schema. So that's one limitation of the existing framework. Then another limitation that we had quite a few years ago now was many people didn't want to use just a fixed dropdown. They wanted to use any subclass of neuron from the cell ontology, for example. Now you could, of course, have some script that will turn this into a fixed static enum in your schema, but that's like very unwieldy to say the least. So we developed a framework called dynamic enums that Damien mentioned. And the basic idea here is that you give some kind of like graph type query that most of the time just is a simple subclass closure type query where you say, I just want to use this branch of this ontology, any descendant following the subclass of edge from the neuron term. And the framework actually allows more complex Boolean expressions, so you can have kind of like a combination of inclusion and exclusion lists. And of course, some people on this call are probably familiar with like frameworks like the Fast Healthcare Interoperability Resources, FHIR, which has a similar mechanism. They call them, I think, intentional and extensional value sets following relational database terminology. And then a relatively new feature that some of you may not be aware of at the moment is this concept of bindings. And the basic idea here is that maybe I want to actually make use of term objects in my ontology rather than just having a string value that binds to a controlled vocabulary. I might want to have have terms be first class in my ontology. I have term objects that might have ID and label properties shown here, kind of on the right. But I want to bind the values of fields in that to terms from ontology. So you can actually do this using this bindings construct. So, so the basic idea here is we've got maybe a single cell experiment. We've got an ID for the experiment, and then the experiment is maybe a single cell type. The value of cell type is not a simple, it's an actual term object here. And actually, to make this more compelling, this probably should have been declared as being inlined. And then just using the normal kind of like LinkML formalism, that would constrain your cell type to be a term object. But with this bindings feature, you can actually kind of like peek inside that object and say, well, the ID value of that must come from this this neuron type enumeration. Someone might need to mute. I can. I think I'm actually able to do this myself. So.
Sorry, done.
All right, excellent. Yeah. Right. So, so some of this has already been presented on calls before, but what we've not had before has been we've had some gaps in how best to check and validate this data. So you can imagine having maybe your sample table, and you're using your dynamic enums, and unlike a static enum that can be checked very easily on runtime just using the schema, it's a bit more of a challenge to check dynamic enums because you have a dependency on this external object, this big, possibly large, hairy ontology object. So just using the core components of LinkML, you don't get the guarantees that you would like for constraining the values of things like the cell type field. We have, do I have something on BS? Maybe we'll come back to it. But also with this kind of like bindings concept as well, or maybe there's many cases in, we see this kind of pattern a lot where you have maybe some kind of like object with kind of like ID label pairs within your schema, within your data sets. This kind of pattern, you can also see it in things like kind of like robot templates as well, where you have a tuple of an ID and a label. And at the moment, just using purely a static schema, you don't really get a way to tell if your label gets out of sync or does not correspond precisely to the ID that you're using. So this is where this new linkml-term-validator comes in. So this, at the moment, it's a standalone tool, but it can also plug into the existing LinkML validation plugin framework. And there's actually kind of 3 plugins with somewhat related functionality, but it's worth kind of like enumerating what they are separately. There's a permissible value meaning plugin, a dynamic enum plugin, and a binding validation plugin. So these all work by using the ontology access kit. The ontology access kit is itself acts as kind of a kind of like a mediating layer, and you can use Oak to validate against either SQL representations of ontologies or BioPortal or the ontology lookup service or files and so on. And so I won't go into kind of like Oak in too much detail here, but I will just talk a little bit about the different plugins and their use cases. So the first is this permissible value meaning plugin. And this is not for validating data. This is for validating schemas. This validates the meaning fields in your static enums. So again, going back to that Kebi example, how do we know that those nanomaterial Kebi IDs correspond to the actual labels that we produce here? Well, now you can use this this term validator against the schema, and it will tell you if it'll give you a report if things get out of sync. And the way it actually works is it will kind of like make use of both the permissible value itself and any annotations on the schema. So sometimes you do want your permissible values to be different from the value, the RDFS labels that are in your ontology. There's many valid reasons for that, but you can always kind of put some kind of like annotation on the permissible values that allows it to map to the label, and that will give you this this an additional layer of checking here. Then probably the one that is kind of like of most value to people using dynamic enums right now. Previously, you had to use something called a VS Kit, which would essentially expand your schema in place. And this would mean that you would make in the cell type example or the neuron example, it would make a new version of your schema with like 1,000 values in your permissible value set all kind of enumerated, which is a little bit kind of like clunky, and it poses various kinds of challenges and so on. But the basic idea with the dynamic enum plugin is that it will actually do a runtime check against the ontology or a cache of that ontology to make sure that the values are correct. And then there's also this binding validation plugin, and this checks essentially these nested objects against binding constraints. So if you might have a schema with maybe some Go functional annotations or pairs of gene IDs or gene symbols in this case, which you wouldn't actually do, and Go terms. And in this case, if somehow the ID and the label get out of sync, it will check, and it will give you an error that will tell you this is the case. So the moment you have like something like dynamic enums, you're presented with this challenge about the fact that ontologies are themselves not static; they are changing all the time. So what do you do if your data validates against the ontology on one day, but then on a subsequent day it kind of like fails to validate? This can cause some change in the ontology kind of like breaks things. So this can cause a lot of churn. So one thing that this framework gives you is the ability to essentially cache the lookups it does over the ontology. This is also very nice for use in kind of like a CI frameworks as well, where you don't necessarily want your GitHub Actions to be doing dynamic lookups of large ontologies all the time. You run this ahead of time. It kind of like makes some cache files, both of the terms themselves and of the enums of the dynamic enums. While you can use this library directly, you can also use it as part of the existing linkml validate command. So the way that linkml validate was written, originally by Patrick Kalita, it uses a very flexible plugin framework, and you can configure this framework at directly within Python, or the more linkml-esque way to do it is essentially with a YAML file. So in your schema directory, you might have something like validation config YAML. It's got a list of all the different plugins and their configurations. So you can kind of configure the JSON schema validation plugin. That's very standard. But then there's these two new configurations that you might want to have. So for the dynamic enum plugin, you might tell it that for connecting to ontologies, it might want to use the semantic SQL database. You could change this. You can actually configure this on a per prefix basis if you like. You can configure the caching and so on. And so this then will all work within just the standard kind of like a LinkML validate framework. And so this, this was all kind of like design, the original designs for this kind of like go back, a number of years. I think this kind of dynamic enum checking, this kind of checking for kind of like ID label pairs are just generally useful within our ecosystem. But one particularly pertinent use case here is something that we're starting to call anti-hallucination checksums. And the basic idea here is that many groups are moving more towards using agents and LLMs to generate data that conforms to a schema. This is originally the kind of paradigm in OntoGPT. People are increasingly moving more towards agentic ways of doing this. And it's well known that LLMs do hallucinate, especially if you kind of like ask them questions in a certain kind of way. There's numerous papers about hallucination of medical code IDs or PubMed IDs. Now, of course, these hallucinations are, so-called hallucinations, are vastly reduced if you use an agent carefully in combination with something like an OLS MCP or a PubMed skill or something like that, where the search results include the IDs and they're part of the agent's context. Nevertheless, there are scenarios where hallucinations will slip out. So you want to, if you are using this kind of workflow, you do want to have some additional level of deterministic validation in your agentic harness. And so the basic idea here is that if you do have some kind of schema that is going to be used by an agent to generate data, then try and always have this kind of like checksum type pattern. And so the idea with ontology terms is, rather than just asking it to make you a Go ID, which is, you're just asking for hallucinations that way. Instead, you ask it for an ID and a label pair. Now, of course, it could still make things up or give you something that doesn't make any sense here, but it does actually mitigate a large class of hallucination errors because you can then deterministically check if the label and the ID make sense together. So that's the there's some separate documentation there on this general pattern. There's another framework we're not talking about today called LinkML Reference Validator that can do similar things for PubMed IDs and DOIs. So we're actually making heavy use of this pattern in our existing DISMEC knowledge base that is actually making use of about 16 different ontologies. There's many different ontology terms on every disorder in DISMEC. And then another use case is this value sets repo. So this is a project where we're trying to aggregate together common value sets that are used across a variety of domains, not just the biosciences, but physical science, data science, healthcare, geography, and environmental science, and so on. So we're collecting a large set of enumerations that are useful for these domains, and we are mapping all of the permissible values to ontologies where possible, and we want to make sure that those mappings are correct. So using the schema validation component of linkml-term-validator gives you an extra kind of like a sense of confidence in some of these mappings. So with that, I'll just leave the URL for up at the moment. It's not considered part of the LinkML core at the moment, but you can find it in the LinkML repo and also in this LinkML.io, LinkML-Term-Validator. We have all of the standard make docs type documentation there. And so with that, I think I'll pause and take any questions. Oh, I see lots in the chat. Mhm.
Go ahead, Philip. Yeah.
Hi, sorry, it's the first time that I can join the LinkML community call, so thanks for both presentations. Great. I was wondering, so far my knowledge was that the bindings feature was not really implemented in the runtime, right? And especially now I just need this validator framework for them to actually make sense, right?
Exactly, yeah. And the reason it's not in the runtime is because it would get kind of quite gnarly to have a dependency on ontology APIs can get very complex, so you don't really want the runtime carrying about that by default. And so it's still somewhat yeah, separate, but it's part of this kind of plugin framework, so you can run this as a separate step right now. Mhm.
So if I understood you correctly, I do not need to have Oak anymore. Just need the bindings validator, and then I'm all good.
It will use Oak behind the scenes, but you can, yeah, using Oak, you can choose to say I want to validate using some files. I am taking control of syncing on my laptop, or I'm going to use an external service like OLS or BioPortal and so on.
Cool. Thank you.
Corey.
Corey.
Thanks. This is great. A thing that's come up for me in some of my work, and this, it's not, I will admit that this is not a clean solution, but it's also just kind of an annoying but real use case, is that a lot of my situations where I have a use case for enums, there is the real possibility that there will be data that falls out of that enum that I'll need to support. And the way that I'm currently doing that is I'll have a pair of slots. One will be the fixed constraint with an other. The other will be the custom value that maybe I'll have a rule set up to conditionally, fill in that field. I have thought about maybe switching that paradigm, and I didn't think that enums could support this, but looking at what you presented today, it feels like maybe this could be useful for this use case I'm talking about, is to actually use like an ID label pair where you basically drop the ID, and in RDF it would turn into a blank node essentially if you're dealing with a non-fixed value. So just curious if that sounds like something that I should be thinking about as a potential use case, or is that beyond sort of the scope of how you guys are thinking about this this bindings?
Possibly, yeah. I don't understand. I'm not quite following why it would make a blank. I mean, the conventional way you would use this bindings is with some kind of term object that would have an ID that would be declared as an identifier, thus making it more like just having in RDF. This would be, you'd probably want to map it to an OWL class or something like that. So
Yes,
it would, yeah. So I think it's still potentially useful for, if I understand your use case, there might be, it's not the case that you want to admit arbitrary string values, but maybe there's at runtime, there's other OWL classes that might be valid values, or yeah.
No,
Yeah.
unfortunately, it is that it's that we've got our fixed list, which whenever
Yeah.
it's using that, we're happy with that. But there is the reality that sometimes there will be arbitrary string values that maybe later will
Yeah.
get folded into some term list or something.
Yeah. Yeah. Yeah, I think it's a slightly separate use case. There's some discussions going way back, to this concept of an open enum list and so on, but that was we never kind of like reached a kind of like consensus on the best way, whether that was even desirable or the best way to implement that. But have a look also at the binding spec as well, and particularly how it pertains to this idea of I think the terminology comes from FHIR, like an obligate binding versus a kind of recommended binding. So that might align with your kind of like use cases where you can then say, well, I want to be fairly open, but I want to kind of like give some kind of ranking and say kind of like this one is, gold star data that uses the enums I've defined.
Great, thanks. Quick follow-up. Should I, if I'm a user of VS Kit and VS Kit Expand, should I be seeing this new set of tooling as like what I should probably be transitioning to?
That's a good question. So I think VS Kit it's clunky, but it's still very useful for when you want to distribute a version of your schema that is where you have fixed within that version of the schema, no matter what happens with the upstream ontology, it will be, data that conforms on V1 will always conform on V1. So that use case will remain. And underneath the hood, they're essentially using the kind of the same code anyway. So.
There is still the Damien's open question in the end, I think.
Sorry, I didn't catch all of there was a lot in chat, so.
Just the last, I think that's the last. The other ones are addressed, I think, as far as I can see.
Yeah, just briefly, I'm interested in seeing LinkML concepts of foreign key, primary key, reflected in the LinkML constraint language. And I'm a little confused at the moment about where all of that stuff is laying. And this idea of this binding validation to control these or put constraints on ID label. That sounds like a primary key, foreign key kind of relationship. So I'd like to see all of this stuff documented to see how it might work together, or how we might be overlapping a few concepts that could be merged.
Definitely, yeah. But quickly, I would say obviously the concept of foreign keys are already baked into LinkML. Forget ontologies for the second. You have an inline reference to something. That if you translate that to a relational schema, boom, you've got a kind of like a foreign key. So that if that is not clear, we should definitely kind of like work on the documentation, both for the SQL generator, which is where the kind of classic foreign key concept comes in. I think the use case here is a bit different. You can think of it as being an outwards facing foreign key that is something that is, it's a kind of like general pattern that kind of like shows up a lot, where you want to have some kind of pointer outside the schema into kind of other data that may itself be fairly dynamic, and you want to kind of like, and it may be quite large, so you want to be able to kind of solve that in a general way. So but anyway, let's follow up on a discussion around Slack.
Right. I certainly appreciate that whole idea of caching and kinds of caching. That'll be great to see that working.
Yeah, I was imagining having a sort of closure table where you've got sort of where you could have a database constraint that is equivalent to a dynamic enumeration by, like, populating two ancestors on a term and all that.
Mm-hmm. And yes, the concept of a term in linkml-term-validator is very flexible. As we maybe controversially in our world, sometimes we treat genes as terms. It's a term that is in the HGNC in quotes ontology. So the framework should be seen as being something kind of like quite flexible that way, for being able to kind of point at any kind of external entity that is managed by some kind of ontology-like framework.
All right, we are at time. So thank you, Chris, Damien, and thanks to everyone for coming. We'll see you next month.
Thank you.